Good day, ladies and gentlemen. This is MTS 102. The course title is still Introductory Mathematics 2. Today we are moving to study section 7. Study section 7, which is application of integration. Application of integration. Here we have the objectives of the section. That is, by the time you might have studied this section or this unit, you should be able to understand the concept of application of integration. So here we have the content. That is, these are the concepts we are going to be taking one by one. That is, we have area under curve, areas under curve, areas beneath a curve given in parametric form, mean value of a function between 2 points, root mean square values, and volume of solid of revolution. So we are going to be looking into all these one by one. So we now move to the definition of terms here, where we have the introduction of the application of integration. In mathematics, the process of integration is used to compute complex area-related problems, whether they are curves or a curve between lines. This can be done easily. Application of integration is essentially useful for engineering, science, and mathematics. So here we have the learning outcomes. We already explained that in the previous slide. So now we want to look into areas under curve here. Looking into this diagram, so we have y-axis, x-axis, then we have the shaded portion from A to B. That A to B is the boundary values. That is, A from A to B, we've given it given as boundary values, and then the shaded portion, you can see that the curve fall on y-axis, that is the positive y. It fall on the positive y. So we have y equal to f of s there. So to now explain this further, to find the area bounded by the curve y equal to f of s, the x-axis and the ordinates at s equal to a and s equal to b is given by a equal to integral y ds. That is, the boundary value is given, which is from A to B. We have the A which is the area under the curve, then which is equal to the value of y there, that is the integral y ds, and the boundary value is from A to B. So and the interval is given. So now to understand this one better, now we are going to look into the example under it. We are looking into this example, that is where to find the area under the curve y equal to s squared plus 2s plus 1 between s equal to 1 and s equal to 2. So looking into this, y is given as s squared plus 2s plus 1, and the limit, which is the intervals, and we also call it boundary values. It is also given from 1 to 2, from 1 to 2. So we now want to substitute into this formula now. So we have a equal to integral y ds. So the boundary value is from 1 to 2, and the y is what? Is s squared plus 2s plus 1. So we now integrate. We integrate it, and when we integrate s squared, we have it as s raised to power 3 over 3. When we integrate 2s, we have it as s squared. Integrate 1, it is x. Then with the addition of arbitrary constants. So now substitute the intervals given. that is from 1 to 2. Anywhere you see x, substitute 2 first. So we have it as 2 raised to power 3 all over 3, then plus 2 raised to power 2 plus 2 plus c. So the answer there will give us 8 over 3 plus 4 plus 2 plus c. Then minus, we now substitute the other value, which is 1. Then put the minus sign there into that bracket. If we substitute 1 into that integral values, we have it as 1 over 3 plus 1 plus 1 plus c. Then we evaluate and get our answer as a 4 odd number 1 all over 3. So the other example we have find the area integral 4 exponential 2x dx from -1 to half. So the interval is given also, that is the boundary values from -1 to half, and we are now substituting back to that formula where we have a equal to integral y dx, and the boundary value from a to b. We substitute back to that formula. You know, a is -1 and b is half, so, and y is 4 exponential 2x dx. So we now integrate. So when we integrate, take the constant outside the integral sign, which is 4, and we now integrate exponential 2x dx. If we integrate exponential 2x dx, we have it as exponential 2x all over 2. How do we got that? We differentiate that 2x there. If we differentiate 2x, you are going to get 2. So that is that value 2, we are dividing it through by everything. So we now the real value will still remain. So we have it as exponential 2x all over 2. So that is how to integrate the exponential function. So we now substitute the limits given. It is the limit of the integrals given, which is -1 and the half. So anywhere you see s, you substitute the intervals given. So if you substitute half to exponential 2x, we have it as what? Exponential 2 multiplied by half. So you know that 2 and half will cancel out, so we are left with exponential. Then so after substituting that, you now put the sign of minus and substitute the -1. So we have it here. So as 2 into exponential minus exponential minus 2. So answer is equal to 2 into exponential minus 1 over exponential. So that's 1 over exponential, we have exponential 2, because if you are rewriting exponential minus 2, we have it as 1 all over exponential 2. So it is that 2 is omitted here. Please put it. So you put the square unit. Then the next example we have, if s is equal to a sin theta, y equal to b cos theta, determine the area under the curve in between theta equal to 0 and theta equal to pi. Now you know that the area under the curve given is equal to integral y ds, and from the question you have y equal to b cos theta, and you also have s equal to a sin theta. So definitely now we are going to integrate with respect to theta. So we need to now change the s here, change the variable, so in a way that we can get it as theta. So therefore you now go back to the question, take s equal to a sin theta and differentiate. If we differentiate it, we have it as the s over the theta will be equal to a cos theta. So now we now take the s as the subject of formula, because we are looking for the for the value of the s. So we take the s as the subject of formula, which is equal to a cos theta d theta, a cos theta d theta. So you now substitute back to the formula. From the original formula we're having, you know, it is integral y ds, integral y ds. So y is already given, substitute the y values, which is b cos theta, then we are changing the s. The s now will now give us a cos theta d theta. Then you substitute there and evaluate. So if you multiply it together, we have it as ab cos square theta d theta. Then take ab outside the integral sign, then integrate cos theta d theta. So when you're integrating cos theta d theta, you are going to get theta over 2 plus sine 2 theta all over 4. Now put in the arbitrary we put in the intervals, that is the boundary values given, substitute into the integral values that we are having there. So anywhere you see theta, substitute pi. That is the first value we are going to substitute. Substitute pi, we have pi over 2 plus sine 2 pi all over 4. Then into bracket minus, anywhere you see theta again, we substitute 0. We have it as 0 over 2 plus sine 2 0 all over 4. Then we will do the evaluation and get the answer as pi ab all over 2, pi ab all over 2. So that is the answer to that. So we are moving now. Now we want to take notes of all this on areas, that is area under the curve. We're going to look into this number 1 diagram. Let's look into this number 1 diagram. You know, we see the curve fell on the what? On the positive y-axis. It fell on the positive y-axis. So it is shown in the above figure that integral f of x dx from a to c plus integral f of x dx from c to b is equal to integral f of x dx from a to b. So that is because it is on the positive side of y. So that's why we're having the addition as this, and it becomes the integral f of x dx from a to b. So we look into another one, which is number 2 diagram. You can see this, looking at this one, you see the shaded portion, the curve fell on where? The negative side of y, the negative side of y. So we now, if y is negative in the range a to b, then the value obtained from the integral f of s, the s, will also be negative, as the s is essentially what? Positive. So thus, the numerical value of the area shown shaded will be minus integral f of x dx from a to b. So because it fell on the negative side of y, that graph, you can see it where it was shaded, it was on the negative side of y. So that's why it contains what? Negative minus sign. So looking at the next one, which is the number 3 diagram. So looking at this one, we see the shaded portion both on the positive y and on the what? Negative y. So if the range includes both positive and negative value of y, the total area must be found in 2 parts and will be integral f of x dx from a to c minus integral f of x dx from c to b. So you can see how this one looks like now. So it's one, you find one shaded area on the positive side of y, and you find another one on the negative side of y. So one will definitely carry positive and the other will carry negative sign. So that is the explanation on that. And the integral f of s ds from a to b, in this case, will give the algebraic sum of the two portions. It is wise to sketch a graph before integrating. At times, if you see any question and you try to sketch it, you see where the graph, where you have the graph and where it falls, then you'll be able to know whether it is on positive or negative side. So therefore, it is very, very good to have a sketch of what you are doing when you are doing this particular course or this particular unit, or when you are doing any work on the area under the curve. So we now move to the next one, which is the number 4 diagram. So looking at this one now, you will see that the curve is at where you find it on the x-axis there, but looking at the range, the range is on where the y-axis. The range is on the y-axis, A to B, from A to B. So now the area between the y-axis and a curve and the line y equal to A and y equal to B will be s dy. So just looking at the one we've been treating, so we see that it is integral y ds. But if you look at this graph critically now, that is number 4 diagram, you will see that the range was found at where y-axis, and we are now looking to the integral at what? At x. Therefore, it is integral s dy. Integral s dy. So this can be proved in a manner as before. So that is about this. So now, when you see any example on this, you'll be able to understand better. So we are going there. Then number 5 diagram. Now, look at the shaded portion here. We have it at both y equal to f of s and y equal to g of s. You will see that y equal to f of s is above that of y equal to g of s. That means the value of that of f of s is always above the values of what? G of s. So let's now look into the explanation very well here. The area between any two curves y equal to f of s and y equal to g of s is easily found if the intersection points or the limits are known. So you can easily find it if you get the intersection points or the limits. So you will see that at times, if the values are given here and you are able to get the point of intersection there, and you get the values, the limits, the intervals, then you now see the one that is above and the one that is below. And with that curve, we know that y equal to f of s is above y equal to g of s. So the area below y equal to f of s is integral f of s ds, and y equal to g of s is integral g of s ds. So the one above is at what? Y equal to f of s, and the one below is what? Is that of g, y equal to g of s. So you can see the integral there, the one containing f of s and the other one containing what? G of s. Hence, the enclosed area shown shaded is the difference between the two areas above. That is, we now have it as integral f of s ds from a to b minus integral g of s ds from a to b. So, and the one above has to be greater than that of the one below. So that is why we have it as f of s is always greater than that of g of s. So that is the assumption there, the assumption here. So f of s is greater than g of s, since f of s is the one above and g of s is the one below. So that is about that. We now want to look into this example now under what we have been explaining. So find the area between the curve y equal to s square minus s. Find the area between the curve y equal to s square minus s and the x-axis, and the ordinate s equal to 0 and s equal to 2. So this one now, we have the solution. We can analyze the curve. We can analyze the curve here. Looking at the curve, you know, s is from 0 to 2. From 0 to 2. So now, let's now get the graph here. You will see that from 0 to 1, you find it on the negative side of y, and from 1 to 2, you find it on the positive side of y. You find it at the positive side of y. So, you know, if you want to plot your graph, you can start input when s is 0, substitute to the value of y given. You have y to be 0. When s is 1, substitute to the value given, then you have it as 1. So when s is 1, we have it as 1 square, that is 1 minus 1, is still 0. So that's why we are having the graph, when s is 0 and also y is 0, and you find the graph on that side of negative y. And when s is 2, y is also 2. Y is also 2. Then you find the graph on the positive side of y. So now the curve crosses the x-axis where s is equal to 0 and s is equal to 1. Hence, the total area numerically, we have it as equal to minus integral y ds from 0 to 1 plus integral y ds from 1 to 2, just as we have seen that graph. It's from 0 to 1 and 1 to 2. So this is how it's going to look like. So we now have the evaluation of it. We substitute the value of y given. Then one is negative, the other one is positive, because one graph is found under the y under the negative y-axis. We find that one on the negative y-axis and the other one on the positive y-axis. So that is why we have this as negative, that is minus integral s square minus s from 0 to 1 plus integral s square minus s from 1 to 2. So now we now evaluate, we just integrate and substitute the value of intervals given from 0 to 1 and from 0 to 2. Substitute back to the integral values and we get the answer as 1 unit square. 1 unit square. So the answer will be 1. Then put the unit, which is unit square. Now, the next example we have it as determine the area bounded between the curve y equal to s square and the line y equal to 4s minus 1. Determine the area bounded between the curve y equal to s square plus 2 and the line y equal to 4s minus 1. You can see we're given curve and we also have one of the straight line, which is 4s minus 1. So two y's are the two values of y are given here, which is s squared plus 2, the curve y, and the line y. So how are we going to go about this? So to determine the area bounded between the curve y equal to x squared plus 2 and the line y equal to 4x minus 1, so we need to set the two expressions equal to each other. We set the two expressions equal to each other to find the point where they intersect. So that is how we are going to go about it. So we now get the intersection point now. That is x squared plus 2 will be equal to 4x minus 1. So we have now set the two expressions equal to each other. The two expressions are now what? Equal to each other. So we now evaluate, solve it, and you factorize. By the time you factorize, we already equate it to 0. After equating it to 0, we factorize, then we have the two values of x to be what? S equal to 1 and s equal to 3. We have it as 1 and 2. So from here now, we have gotten the limit, we have found the intervals, we have gotten the range, the interval, the limit of the integrals. So we have gotten it to be what? 1 and 3. So here now you can easily solve and use the formula. Now this is it. We compare the value of the function between x equal to 1 and x equal to 3. Y is equal to 4x minus 1 is above y equal to x squared plus 2. So the line y now is above the curve y, which is equal to x squared plus 2. So we now have it in this form. Then the area enclosed, which is equal to integral 4x minus 1 from 1 to 3 minus integral x squared plus 2 dx from 1 to 3. So we now, since line y is above that of curve y, so we have line y first minus that of curve y. Then we have our answer. We just integrate. You integrate and get the answer to be what? 1 odd number 1/3 square units. So I believe all this you can easily solve it once you are able to determine the area enclosed. You are able to determine the area enclosed. So the remaining are simple. You just integrate, substitute the boundary values, then you get your answer. So we now move to the next unit. That is, we have area beneath a curve given in parametric form. Area beneath a curve given in parametric form. A curve has parametric equation, that is x is equal to 80 squared, y equal to 280. Find the area bounded by the curve, the x-axis, and the ordinate at t equal to 1 and t equal to 2. So this is how you find the given function under this area beneath a curve, that is, which is given in parametric form. So a is given as x is given as what? 80 squared, and y is given as what? 280. And looking at the range is from t equal to 1 to t equal to 2. So how do we go about this? You know that the formula is a equal to integral y dx from whatever the variable you use. Here we use alpha to beta, from alpha to beta. So that alpha and beta here, they are the range, from range alpha to beta, that is the limit of the integral or the boundary values. So now, since it is given a parametric equation, you will have to change the variable, the s, where you can find it as t. So how do we go about that? We need to differentiate s equal to 80 squared. So I believe we have done something related the other time, but you differentiate s equal to 8t squared. Now we now get the s over the t as what? As 2at. 2at. So we now make the s the subject of formula. If you make the s the subject of formula, you have it as 2at dt. 2at dt. We now substitute back to the formula. You know, the value of y given is 280. Put it there. Then the value of the s, you know, the s is already what? 280 dt. Then you just replace with 280 dt. So that's why we're having it as a equal to integral 280 dot 280 dt from 1 to 2. So multiply this together, we have it as what? For 280 multiplied by 280 will give us what? 4a squared t squared. 4a squared t squared dt. So it bring out the constant there, which is 4. Bring it out outside this integral sign. Then we are left with a squared t squared dt. So we now integrate this. And looking at this, a squared there is t constant. Since we are integrating with respect to t, so a square is still a constant. By the time we integrate, then we have a square outside integral 2. We now have it as equal to 4a square integral t squared dt from 1 to 2. We now integrate t squared easily. So if we are integrating t squared, we have it as t raised to the power 3 all over 3. So when you substitute the value, the boundary value, which is 2 and 1. So anywhere you see t, substitute 2 first. You have 8 over 3, where you minus, where you see t, substitute 1 again, which is 1 over 3. Then the answer now is 28a squared all over 3, because by the time you evaluate that, do some mathematics, then you get your answer as 28a squared all over 3. So that's about the example on area beneath the curve given in parametric form. So now we move to another unit now, which is mean value of a function between 2 points. It's another subtopic here. We have it as mean value of a function between 2 points. So here we have the mean to be equal to area all over base value. Area all over base value, and area is given as a, and the base value is b minus a. So we have it as a all over b minus a. So now to get the mean value function now between 2 points, then we have it as n equal to 1 all over b minus a, while the s, that 2 point there is what? From a to b, from a to b. So it is equal to n equal to 1 over b minus a integral y ds from a to b. So any question under the mean value of a function between 2.9, then we have any question there, you just substitute into this formula. Now let's now substitute that the value we are given. We substitute where we see y, substitute 3 sine 5t plus 2 cos 3t dt. Then the interval is from 0 to pi. Then you integrate, and we have our answer to be equal to 1 all over pi. 1 all over pi. So that is that. Now we move into root mean square values. Root mean square values. So here we are looking into the root mean square values, where we have the root mean square to be equal to square root mean value of y square between a and b, Then here root mean square, if we scale both sides, we have this square root we cancel out, and we now have root mean square, that is all raised to power of 2 there, equal to mean value of y square between a and b, and it is equal to what? 1 all over b minus a integral y squared ds from a to b. So that is the formula there. So we now have this example under it. Find the root mean square value of y equal to x squared plus 3 between x equal to 1 and x equal to 3. Then we have the solution. The root mean square formula is 1 all over b minus a integral y squared ds from a to b. Then you substitute the value of y, then you scale it, put in the intervals, that is from 1 to 3. Where you see a, put 1. Where you see b, substitute 3. Then we now integrate and have our answer. So substitute the boundary values there. We have the answer to be 59.2. So now, since it is root mean square or square, we are going to get this. Now we square both sides and have root mean square is equal to square root 59.2, and the answer, when we have the square root 59.2, we have about 7.69. So we now move to the volume of solid of revolution. Here, if the function to be revolved is a function of s, then the following integral represents the volume of the solid of revolution, where we have a pi integral y squared s from a to b. So when calculate the volume of solid of revolution, we normally use a disk or shell via integration. So this is what you are looking at here. That is, the disk or shell via integration is usually used when dealing with a volume of solid of revolution. So here we have the formula V equal to pi integral y squared ds from a to b. So now look into this example under it. That is, determine the volume produced when the plane figure enclosed by y equal to 5 cos 2s, the x-axis and ordinate at x equal to 0 and x equal to pi over 4 revolves round the x-axis through a full revolution. So here we have the solution. Y is given, the intervals are also given from 0 to pi over 4. So we now substitute into the formula of the volume of revolution. Then we have it as pi integral, where we have 5 cos 2s. We have to scale it because y is square. So the scale it, we have it as 25 cos square 2s ds. Then we take the constant outside, which is 25. We have it as 25 pi integral cos square 2s ds from 0 to pi all over 4. So we now integrate. These are the hints given here. If you want to integrate cos 2 theta, it is equal to 2 cos square theta minus 1. And if you want to integrate cos square theta, it's always equal to 1 over 2 into 1 plus cos 2 theta. And you can at the same time rewrite this as 1 all over 2 plus cos 2 theta all over 2. So just have it, get the integration, then substitute the intervals given then we have the answer as what? 25 pi square all over 8. 25 pi square all over 8. So that is all what we have under the application of integration. So I think we have really done much today. So thank you for listening. Meet you again next time.